in the series that we have seen so far, we could only obtain convergence criteria for cases when all the terms of a series are non-negative. So alternating series is the first example of a series where terms can take arbitrary sign, both positive and negative, but this occurs in a very controlled fashion. So the positive and negative signs alternate, which explains the name in particular. So let me first give you the definition of an alternating series. So an alternating series is a series in which the terms, let's say we have a sum of k from 1 to infinity, in which either ak is equal to -1 to the k minus 1 times some bk, or ak equals -1 to the k bk. Both of these forms must hold with bk's strictly positive. So what this is saying here is that we have signs of our terms change back and forth between plus and minus, and the absolute value bk must be strictly bigger than 0. So let me give you some examples. The first example is k from 1 to infinity -1 to the k minus 1 times 1 over k. So what the series looks like is it starts off positive. So you see that for k equals 1, the exponent at -1 is 0, giving us 1. So we have 1 over 1 minus 1 over 2 plus 1 over 3 minus 1 over 4, and so on. So this is effectively the harmonic series with the signs of its terms changing for every other term, being positive for every other term. Another example, so you can see that it doesn't matter if you start off with a plus sign, or you could just as well start off with a minus sign. All that changes is entire series is multiplied by -1. So we could just as well write down something like so. So we could say we have a series. Let's say we have -1 to the k times k over k plus 1. So what this series would do, it would start off with a minus sign, because k equals 1 now gives -1 to the first, which is -1. And we would have -1 over 2 plus 2 over 3 minus 3 over 4, and so on. So if a series starts with the minus sign, but then we have alternating signs onwards from that point, this still counts as an alternating series. And so it turns out that for alternating series, you can obtain convergence under quite weak assumptions on bk's. So somehow the idea is that, take this series for example, without the alternating sign factor, is just sum of 1 over k, and that's a harmonic series which is divergent. So somehow if it were not for the alternating sign, all the terms would accumulate and the partial sums would go to plus infinity. And what happens in view of the alternating sign factor is accumulation does not occur. Rather, there is some cancellation, because the terms go plus and minus, and so alternating the alternating series has its partial sums going up and down, and they eventually stabilize next to a limiting value. So I will explain this argument a little bit in a second, but first let me formulate the alternating series test. So this test will be applicable to series of the forms that we have just seen. So basically series that involve a factor -1 to the k, or -1 to k minus 1. And if the assumptions of this test are satisfied, we will conclude that the alternating series is convergent. So all you need for an alternating series of the form suppose we have the sum k from 1 to infinity -1 to k minus 1. So it starts off with the positive term. So the argument is exactly the same if it starts off with -1 to the k. So suppose suppose that we have this expression for our alternating series. So clearly here bk's must be positive by the definition of alternating series. So if this series additionally satisfies two conditions, okay, and the two conditions are the following. First, bk plus 1 is less than or equal bk. In other words, the absolute values of terms of our series go to 0. So this is the same. So first of all, this must be true for all k's starting from k equals 1, or starting from some point. So just as before, if this inequality holds not from k equals 1, but from k equals 20, this is still fine. Right? And so basically this is the same as to say that absolute value of ak plus 1 is less than or equal absolute value of ak, if you think of ak as the kth term including this sign. So it's sometimes useful to think of it this way. And the second condition is that the limit of bk's as k goes to infinity is 0. And so what this is saying is that the absolute values of the terms in our alternating series must be decreasing. So every next one must be less than or equal the previous one, and the limit of bk's must be 0. So the length of the terms in our series go to 0. So let me draw a picture illustrating this test. So I would like to illustrate it. So let me draw the number line. So here is the real numbers, right? And let's show here the partial sums of our alternating series. So we'll start with 0. So we want to show partial sums of the series sum of, so let's say these are partial sums of the sum -1 to k minus 1 bk, right? And we are assuming that the two conditions from alternating series test are satisfied. So the absolute values bk's are decreasing, and they go to 0 as k goes to infinity. So we're going to depict the partial sums. So let's start with S1. So S1 is simply the first term of the series. We see it's positive. Its absolute value is equal to B1. So this here is S1. Now, the second partial sum is the sum of the first two terms in our series. The first term is positive, so the second must be negative. And so if I think of the first partial sum as basically a vector that starts at 0 and goes to S1, like so. Right? So if this is the first partial sum, then the second partial sum is the sum of this vector, which shows the first entry of the series. Then I have to subtract the I have to take a vector that goes in the opposite direction, because the second term is now negative and it has length b2. So S2 is going to be shown by a vector that starts at the value S1 and ends up over here. So this is the value S2. Right? So what happens, I'm going to show it here on the graph, like so. So the first term brings us from 0 to S1. The second term, we have the second partial sum is the first plus the second term, so it brings us to the left to this value S2 here. Right, then we're going to continue like that exactly. So to get the third partial sum, we need to take the second partial sum and add the third term from our series. We have that the third term is positive, but it's shorter. So notice that what I'm doing here is I'm drawing a shorter arrow than I do in the second step. So now this arrow will end up being maybe over here, right? And this will be the value S3 of the third partial sum. So first I go right, then I go left, then I go right again, and that's my S3. Now every time I make a little jump, the length of this jump is shorter than the length from the previous step because of this assumption. Right, so this is S3. Now for the fourth partial sum, I'm going to make a jump to the left because that term, the fourth term in our series, will be negative again, and I will be jumping left. Therefore, I'll be also jumping by a shorter distance. So I may end up, let's say, over here. Right, and this means that the fourth partial sum of this series will be somewhere here, for example. So this will be S4. And then I continue like so. So you can now understand how this procedure will continue. Then I will make jump to the right again, and I need to make it shorter than the length of the previous jump as well. So it will end up to the right, it will end up to the left of S3. So maybe over here, right? And this will be my S5 and so on. So every even partial sum will move to the right? So we have S2, then S4 to the right of it, then S6 will be to the right of S4 and so on. Whereas on the other hand, the odd partial sums will shift to the left, right? Just like that. So we have S1, then we have S3, then S5, and so on. So we'll be gradually shifting to the left. And because of the second condition, the length of the jumps that we are making are shrinking to 0. And so that will ensure that the even partial sums and the odd partial sums will meet at some intermediate point, and that point will be exactly the limiting the infinite sum of this alternating series. And so I can now conclude the statement of the alternating series test, which says that if an alternating series of this form satisfies these two conditions, then it is convergent. So these are the assumptions that you need to check for an alternating series. Now, so we studied it for the form in which the first entry, the first term has sign plus, but this applies just as well for an alternating series with the first term that is negative. And so in the subsequent videos, we will look at some applications of this convergence test.